So, hi everybody. Thank you everybody for coming. Today we're going to talk about securing your protocol with the Certora Prover, actually how to formally verify it. So, I'm Pamina. I work at Certora. I'm the formal verification team lead. And Certora is a Web3 security company. And we're doing all kinds of things that you might need for security in DeFi. And especially, we also have a tool called the Certora Prover that can do various things. And today, I'm specifically going to talk about how to use it to verify some smart contracts. And I'm going to try to convince you that it's easy, and if you're a Solidity developer, you can do it too. Okay, so what is formal verification? It is, according to Wikipedia, the act of proving or disproving the correctness of a system with respect to a certain formal specification or property using formal methods of mathematics. Well, that sounds very long and very boring, but what this means, basically, all of your protocols, if you write a DeFi protocol, you have some key invariants, and we can, if you know what your needs are of the protocol that you want to write, right? There are some inherent specifications and assumptions that you make about your code. Now we can formalize them, and we can use mathematical tools to actually show that the way you wrote your code satisfies these properties. And that is exactly what we want to do at Certora with the Certora Prover. So let's start with 2 truths and a lie about formal verification. What do you think the lie is? So the first one is formal verification finds bugs. The second one is formal verification can mathematically guarantee that your protocol will remain solvent. And the third one, formal verification is hard and requires a PhD to be successful. So what do you think the lie is? 1, 2, or 3? 1, raise your hand. 2, raise your hand. Anybody? Oh, you all think we can do this. Cool, cool. And number 3, anybody? Yes, yes. That's my opinion too. Wonderful. So let's look at the first one. Formal verification finds bugs. Actually, we can find all kinds of bugs, and especially the super strange ones, right? The ones that are not as obvious. So we can find rounding errors that are not super obvious. For example, recently in a project, we basically found a rounding error in a muldiv that was meant, like that used a classical integer-based algorithm for a ceiling muldiv operation, but it was actually used on fixed point numbers. Well, it didn't work out so well because the ceiling just didn't work. Like the ceiling was basically, just didn't do anything. We can find all kinds of strange edge cases. Like, for example, you're in some particular state where you have very, very high values in storage or very low values in storage. And we can all of a sudden see that if you deposit at that particular state, the share value in your system will decrease. That's not something you want. Basically, with any operation you do in a DeFi protocol, you want to make sure that the share value either stays the same or increases, right? We can find bugs with compliance issues. So, for example, recently we had we came across a bug in where there was a protocol. They had a withdrawal queue, like a redemption queue, and they claimed FIFO, right? So if you withdraw, you're going to be in the queue, and as soon as there is liquidity, you're going to get your liquidity out there. Turns out it could be circumvented. We can show that these things are possible. But most importantly, we can also ensure that when you provide a fix, it's actually fixed. Next thing, formal verification can prove solvency. Yes, we can, and we can prove way more than that. We can prove, for example, in lending protocols that well collateralized, like a healthy account that is not that has a healthy LTV, remains healthy unless a pricing action tips them over, right? But not by any user action, you cannot become unhealthy. We did, for example, prove that for the Euler Vault Kit. We proved solvency in Uniswap, but we didn't only prove solvency, we can also prove that your share value does never go down. We can prove compliance, things like we said before about like your redemption queues, that your users are treated fairly. But we can also make sure that if there are rounding errors, that the users cannot take take advantage of that. So those are the cool things that you can do with formal verification. Now I'm trying to convince you that you do not need a PhD, especially not with the Certora Prover, because the Certora Prover was specifically designed to be simple to use for Solidity developers. And to that extent, we have the Certora verification language. We're going to do a little tutorial after this intro. And in my opinion, if you can write Solidity, you can write formal specs. If you understand what pre and post conditions are, you can write formal specs. And if you don't know what pre and post conditions are, you know what asserts and requires are. That's that. So if you can write code that looks somewhat like this, and I'll explain what the parts of this code are, you will be able to do formal verification. Okay, let me give you a bit of a background into the Solidity part of the Certora, or the Certora Prover in general. So basically, we take your Solidity contracts, we take a spec file, and then we feed this to the Certora Prover, and the Certora Prover will give us either a proof. That means that in any reachable state of your program, the property that we want to verify is actually satisfied. Or we find a weird, rare behavior, like a concrete state with concrete numbers where this behavior is violated, and that is often a bug. Now, how does this work internally? That means we basically take the spec and the Solidity, and we internally translate this to so-called verification conditions. So we translate it to logical constraint formulas, and we feed those to so-called SMT solvers, satisfiability modular theory. That's what's going on in simple terms under the hood. But we're not super concerned about that right now, because you actually don't even need to know any of that to use it. What is very, very important, and what cannot be stressed enough is that we're doing a sort of symbolic execution, right? It's not testing, it's not fuzzing. Even if we write super simple properties that look like a unit test, it's not the same as a unit test, because the prover will look into any possible state, any possible state that is reachable in your program, right? All the inputs are non-deterministic. So it's proved so if you have a UN256, it will be proved for any UN256, not one concrete one. And the same goes for all the different branches, the different computation paths your program can take. All of them are considered. So why do formal verification? You just add another layer of security on top of traditional ones like testing, fuzzing, manual code audits, etc. And what you want to use it for, in my personal opinion also, is you want to ensure the key invariance of your protocol, like the basic ideas that your DeFi protocol, your smart contracts should do. Those should be formally verified to make sure that your users cannot get wrecked. Good. So that means a proof holds for any kind of state, any reachable state of your program. And a counterexample is one particular state that violates it. Okay, some of you saw this already before. We will now go over to the practical portion. I will put my mic here. Please let me know if you can still hear me. Does that work? Can you hear me like that? Okay, cool. So we're gonna do a little bit of a CVL tutorial with some very basic rules. And I'm just gonna jump. So if you open this link, you will see the following tutorial. And you can just jump ahead into the first one if you want and follow along. I'll jump over now to the actual code, right? So the first thing that we're gonna look at is a very simple voting contract. And it just has one mapping. It tracks if the people that voted already have voted, right? It just tracks true or false for each of those addresses. It has votes in favor, votes against, and it counts the total votes. And there's only one function vote. Now, what do you need to do to verify this very simple contract with Certora Prover? You need two things. You need a spec file and you need a conf file. The spec file is where we put our formal specifications. And this is our first rule, right? So this, you can see here, this is basically what this looks like. We have a rule here, vote integrity, that just checks that the total votes are increasing whenever you call vote. Okay, some things are going on here. So first of all, we have the keyword rule. Instead of function, you just write rule, right? You give it some name, like you would a function. Then we have this special environment variable. The environment variable, you can, by the way, you can declare this as a parameter, or you can declare it here, it doesn't really matter. The environment variable gives you all the EVM environment things, right? It can give you, you can have the message sender with e.message sender. You can have the block timestamp with e.block timestamp. Okay, this is just the CVL version of all of these things you already have in Solidity. And basically, what we want to do is we want to save the states of the total votes into a variable before we execute a function. That's the voted before. Then we declare a variable is in favor that we use as a parameter to send to the function. But this is very important. I declare it, but I don't give it a value because it's non-deterministic. So it can, the prover will know this can be any Boolean. Boolean is easy, so it's either true or false. But if this was like a uint 256, let's say, then this would mean any value that uint 256 could have. Okay? So then we call the function. We call the function with this environment because in this case, this function depends on the message sender. So it's important to actually give the symbolic call, the information of the environment. The total votes here, for example, are, so this is the methods block. We can do a bunch of things in the methods block, but for now, let's just say we declare here functions of the contracts that we want to verify. And in this case, we just simply say here, this is end-free. That means I can call this function without passing the environment variable because this is just a getter, right? I don't need any information about message sender or block something. And then we write the assertion. And in the assertion, we could have done also this. Voted after is total votes. Or we can just call it directly in the assertion once more and just make sure that it's more than before. So that's our first rule. Now, the other thing that we need to make sure is we we tell the prover what kind of files it needs to and what kind of things it should verify, right? So to that end, we have these conf files. They're JSON-5 format. Basically, you want to specify here all of the files that are necessary for you to get sent to the prover. And the way we specify it is, so the Certora, we usually put all of the Certora stuff outside of the source directory. And so in this case, we want to use the voting box sol file, but the contract is called voting. So we have this :voting here to specify that we want to use that contract. And we want to verify that contract with the specs that are in the voting box spec, right? We can pass a message. This you will probably not need. I'll need that so that it's not running locally on my machine, but I send it to the cloud. You'll see in a second. And then you pass whatever solc version you use. I personally use solc select, so you can just put here solc. And then we can go over to the terminal, and you just go to the basic directory, and you can run the tool by simply saying Certora run and pass it the configuration file. And so we want to just do that. This is not the super interesting part, right? So basically what's happening here is just compiling the Solidity files and sends the bytecode over to the prover. And then you get here the link to the prover output. So we can click this, or we can do what I usually do, namely go to the job list and see this is the latest job that I was sending here to the prover. And this is what the output looks like. This is too small, I guess, to read, right? You tell me once it's... Is that okay-ish? Yeah? A bit more? Then can I... Okay. So as you can see here, these are the rules. So there are more than just one rule, the vote integrity rule, but there's also this like n-free static check, and that basically just checks that. Why can I not see this now? There we go. It basically just, so the first rule just checks whether these n-free declarations are fine, so that the methods that we're using here are actually not using any environment information. And then we can see the vote integrity has a bug. Nope. And here we have a couple of other views. So first of all, we have this local variables tab. So the local variables tab, here you can also see what you have in E. So we have a message sender that is 0x401 address. We have voted before is 0x3. Usually you get a hex output, but you can also make this decimal, so it's easier to read. So voted before is 3. And here you can see the call trace. So we get a counterexample, and for the counterexample, we get the exact computation path that led to this specific counterexample here in the call trace. So there's a bunch of things going on. Here's like the state that led to the counterexample is set up here. So we see there is in the voting contract, there is a has voted field. We've seen it before. With the address for 401, did not vote yet. The total votes before were 3. The votes against were 590. So we also already maybe see another invariant that we're missing here, namely that the total votes should be the sum of something. And then we can see the native balances of the contracts in the scene, which in this case, what we're looking at right now is not that interesting. Then there's a bunch of setup things happening. Mostly you can ignore this if you want to find bugs or find proofs. But what is interesting is the before and after, right? So if we open this, we can see for whatever reason, the total votes after are 1. So here's like what's happening in the voting. That's the voting before. That's the call to votes. So we can see the message sender is this 401 contract. You can also, let me just make this a bit bigger. We can also jump to source. And then you get, at least so for example, here we can see, here it stores voting total votes 1. So clearly that's the bug. If you guys haven't seen it before, I removed the plus, so we have a bug. And that's basically how it goes. We can see that the votes against increased by 1, but the total votes were just reset to 1, and that's why we have a bug. And then we can, of course, go to our voting bug spec. No, it's not the spec, but the Solidity contract, and fix it, run it again. And check that it's proven. This will take us about a minute. Okay, meanwhile, we've already seen we maybe want to write another property, right? Namely that the total votes is the sum of the votes against and the votes in favor. So I'll start writing a rule. Total vote sum. We will call the vote function. And we want to assert that the total votes is equal to votes against plus votes in favor. Okay. Do you think that this will work?
Can I ask a question?
Sure.
How do overflows play into this?
It depends, right? I mean, if you have, so we model a U in 256 as a U in 256 in the logical constraints. In this case, the overflow is not the issue. So in this case, there is a different problem. So I'm talking a lot about invariance, right? How can we prove that total votes is the sum of the votes against and votes in favor? That it holds in every state. What do we need to assume something here?
Well, we have to work against. That rule is symbolic. So
Exactly. We already do that. So remember, the prover will assume any starting state.
Of course, you have to increment one before the other. Of course, you have to increment one before the other. It's impossible to increment both at the same time. So at some step, you will have one, and the assertion will fail.
But we don't start with a 0 state, right? We start in a random state.
constrain it to a valid initial state, and from there, the resulting state should be that.
Exactly. Could you repeat that with the mic?
So we have to ensure that we start from a state which is already valid. Otherwise, in an invalid state, you can vote whichever way, it'll stay invalid.
Yes. So how would we have to constrain it here? Any ideas? In the back?
Maybe we can constrain. Maybe you have some, I don't know, decorators to constrain to when this rule will apply.
We have requires. So what would I write here? Can you repeat?
Something like contract is initialized or something like that.
It's not the initialization that's the key. We can be in any program state, right? We can be in the middle of, the vote function could have been already executed 100 times.
Is it your assert, but with the assert changed to require?
Exactly. And because it's an inductive invariant, right? And what we're doing here is we're proving not a base case, like after the constructor, but we're proving a step case of the contract. So executing any function is actually, if you think about it in induction terms, mathematical induction terms, it's a step case. So what we need to do is we need to require that we are in a valid state. We need to apply the induction hypothesis. You see? And now we can run it and probably get a proof. I can also pass here -- rule and just run this one particular rule. Now, let's just see. Okay, cool. So vote integrity has now been proven. Our property about the total votes has also been proven. And I just want to show you what happens if we remove this to make it a bit more clear maybe. So the counterexample that we get here looks like the following. So we see the votes against and votes in favor are more or less the same number as the total votes. And that is because in the setup already, it has been set up in such a way that already violates our invariant. Of course, and after calling it once, like the vote function calling it once, will still violate it. So we have to assume we're in a state where it already holds. Okay, now let's say we don't want to write this for every function. Let's say the voting bug contract has another external function, do nothing. That is now empty. But basically we want to make sure that for any function it's verified, right? So we can go ahead and write a so-called parametric rule. So let me just copy this for a sec. So instead of just calling vote here, we want to call any method of the contract with whatever arguments it needs. So rather than declaring here bool is in favor, I can declare some method f. The provable no, it's from one of the methods from the contract that we're verifying. And I can say call data args, and then the provable no use whatever arguments are necessary for the particular instantiation of f that you're currently using. So this way I can basically prove the total vote sum holds for all of the functions of the contract. So if we run this now, so as you can see now, the prover instantiates, actually you can see all of the step cases that we're doing currently, right? So we see it for vote, it's proven, but it's also proven for all of the getters, and it's proven for our do nothing. Of course, the question is this necessary? In this case, it's not, right? Because the getters don't really write to the storage, so it won't change the state. But we actually have something to make this your life easier, and you can, when you have a property like the one that you would require in the cert, we actually have the keyword invariant. And then you can say total vote sum invariant, and then just write the invariant. And if we run this one, So basically, something that the invariant keyword that you will see in a second is doing in contrast to the parametric rule is it will only run this invariant on any kind of function, on any kind of external function that could technically change the state. So no getters, no view functions. And it does that without you having to deal with it, basically. And that we will see in hopefully a sec.
So while that's running,
Sure.
is the thing that it's proving right now, is it proving that the invariant holds at the entry and exits of those functions, or at each intermediate state of the function as well?
So it assumes it at the beginning of the function, and then it asserts it after the function is finished.
Okay, so hypothetically,
Yeah.
the invariant could be violated in the middle of the function so long
Yeah.
as it's restored when the function
Yes.
returns. Okay.
Yes. Yes.
So what if my function theoretically has some point of reentrancy where eventually the execution would circle back in a state while the invariant is being violated? Would this catch that? I'm guessing yes, but
Can you say that again? The
so I
last
made a
word?
terrible mistake
Yeah.
and left a reentrancy bug in my code,
Yeah.
and this can be exploited in a state while the invariant doesn't hold.
Then we would probably find that. Yes.
Right.
Yes. But we also have rules that check for reentrancy.
I'm guessing. Yeah.
Yeah. So the one thing that I wanted to point out here, the reason for why I was waiting for that run is that the invariant keyword also checks the constructor. So that's the difference between a step case and a base case. I have it outlined, I think, here. What I want you to understand is what we're doing under the hood is structural induction. So let's say we have a contract with a constructor. The constructor is our base case. So that's what you were referring to. We initialize the contract and then we just assert it. We do not require anything on the initialization. We want to make sure once the contract is initialized, it's actually the invariant is satisfied. And then for any of the external functions that can change it, we assume that we're in a state, because the base case already proved it, right? That we start in a state where this is satisfied. So we require it, we execute whatever function, symbolically, of course, and then assert it again. So it's nothing else than an inductive proof. Cool. So that's the first part. Can you read this, by the way? Let's move on to something a bit different. It's another toy example, but it's a bit a different one. It's a minimal token in an ERC20 style, let's say. It has a mapping for balances. It has a mapping for allowances. It has a total supply. It has a transfer and a transfer from function. And it has an approve function. And it also has a deposit function. And this deposit function is a payable function. So if you want to deposit to our minimal token, you need to pay for whatever amount, like the message value needs to be bigger or equal that amount. And that is then put into your balances of the message sent and total supply is increased, et cetera, et cetera. I think you get the gist. And then we have here our small little spec. So we declare again, we use balance of and total supply here. So we declare balance of and total supply as and free because they're just getters. And we have two invariants here. First of all, we want to make sure that the balance of the zero address, so we don't need to cast to address here in CVL, we can just use the zero directly, is 0. And then we want to prove a token solvency, namely that the ETH balance of our contract minimal token is at least as much as its total supply. Make sense? And this native balances keyword is our nice CVL way of saying that's the ETH balance of whatever address you put here. In this case, we have this keyword current contract as well. That will basically be the contract that you put in your verify clause in the conf file. So in this case, the minimal token. Cool? Okay, now let's maybe run this. So we see, cool, the first invariant that the 0 address has no balance is satisfied in every state. However, we found a violation in the token solvency rule. So let's check for which function. The deposit function. So let's see what's going on in the call trace. Basically, let me just put this back to decimal here. So we assume the invariant in the pre-state, right? So we have a very large token balance of minimal token. We have a little bit of supply. And clearly, the balance, the ETH balance is bigger than the total supply. And then what we want to ensure is that the minimal token balance is still bigger, equal to total supply, which is not the case anymore here. Now, why is this the case? So we can see like something happened weirdly in the deposit function that made our total supply explode, right? That is clear, I hope. So we can check the effects of one of the steps taken, which is the deposit function. So we can see what's happening here. So we see there is an amount deposited that is really, really large. But if we look at the balance before and after, even if it's very, very long numbers, I think it's clear that they're the same. We can actually maybe see this here, or not so well. So you can see, basically, this is the same as this number here, right? And all of a sudden, this is almost the same too. So what do you think happened? What do you think is the bug? Yes?
You're having the amount when you transfer message value, but you adding to the mapping amount, so you can transfer any amount that you want and transfer less, for example,
But
message value.
But how is it possible that the total supply increased, but not the value, not the balance?
Yeah, but you transfer, like, the function
This is the
payable.
function, right?
Yeah. So you basically, I don't know, maybe because you.
So we use this amount, we increment both values with the same amount, right? So why did one increase and the other one did not? Can anybody think of such a situation? Good idea, but no. It's not an overflow issue. Think about the message. Who can be the message sender? Any address, right? Sorry, I'm not hearing it. And any address can be the message sender. So how do you think it's possible that if we send this amount,
Like you initialize
the constructor of the deployed contract, you are doing like deposit. So you are calling to deposit when you are deploying new contract, and the constructor.
You're thinking even you're getting. I think you might be getting in the right direction, but you're thinking way too complicated. If you call deposit, and just one of the values, and this is a payable function, right? So whoever calls this, it's gonna remove the amount. Right, from
Reentrancy? If the same contract
It's also it's not reentrancy. It's not that.
Is the contract the depositor?
Yes, exactly. That's the correct answer. So the actual contract that we're trying to verify here is the message sender. So it pays to itself, which increases the total supply, but not the balance. Make sense? Any questions on that? But we can actually see this in the counter example. So let me just see. It actually says it here. So sender is minimal token. And then what happens here is, okay, the message value is big enough, And then, of course, it's payable, so it removes it from the native balances, but it doesn't, and then adds it again, and it adds it to the total supply, but the native balances won't change. Cool? So that's one of these examples. Okay, I have one final example for today, which is a bit of a different contract. What do we have? It's the power voting contract. So the power voting contract now is another voting contract, but it uses our minimal token. And so the idea is now you can vote with the amount of money that you have. Okay? So we have a mapping amount voted. We still have the mapping has voted. We still count the votes in the votes in favor, votes against. We have now the minimal token. We call it token. We still have like total votes. The total votes now are now based on the balances in our minimal token. So the total votes are is the token balance of our current power voting contract. Voting has some period here, so there is a way of ending the voting period, and the voting power is the token balance of the message sender. Okay, so let's see our spec. We use, again, the vote integrity rule that we've seen before, that the total votes are increasing if somebody votes. And we have also the sum invariant. And just let me show you quickly how we set this up here. So we have in the power voting conf, we say that we have to include, first of all, we have to include both files. So the minimal token fixed, or in this case, we used a fixed token, okay. So we have to include both files, both contracts, and we can then say in the power voting contract, the token is meant to be the minimal token. So this tells the prover to resolve any calls to token to the actual external functions that are defined in the minimal token. And then we can go ahead and run this. In the meanwhile, let's fix the other problem. So what is the problem with the function in the minimal token? We're missing a requirement here, right? We're missing that the message sender shouldn't be address this. Nope, I'm running the wrong spec. Sorry about that. By the way, if you want to like look at this after as well, or just keep continuing, we actually also have all of the rule reports here in this little tutorial. So you can see it here too. Now let's see about the output. Okay. So we see we get some violations here, right? The first one is the total votes did not increase in this very, very simple rule, right? So we can see here somebody calls vote, but the total votes did not increase. Total votes before, after is 14, and before is also 14. So one of the issues that just jumps at you here is that the transferred amount, remember the voting function now needs money, right? If you don't transfer anything, you're not voting, basically. You can still call the function, but the transferred amount is 0, so it won't have any effect. So in this case, actually what is happening is our specification changed. So it's not a bug necessarily in the contract, but we might want to make sure that if the token balance is 0, the total votes before stays 0. And if the token balance is actually greater than 0, the total votes is bigger than the voted before. So we can also have multiple assertions in one rule. And then if we rerun this part, it's called voting and vote integrity. What did I do? Oh. So this should work out now because we take care. Now let's see what the other invariant did. So we see that the total votes is sum invariant is also violated in one or more of our step cases. So what I did here is another step. So we can see we can actually run our invariance not only on one contract, but on multiple contracts. In this case, we want to run it on the power voting itself, but also on the minimal token. And we can see that any kind of method that transfers any tokens in our minimal transfer actually has some issues here, and find some counterexamples. So let's try to understand what's going on here. So we assume the votes in favor is 0, votes against is 2, total votes is 2, so great, the sum is fine. And then the votes in favor is still 0, votes against is still 2, but the total votes is 3. So what do you think happened here?
Did someone just directly send tokens to the
Yeah,
voting
someone
contract?
donated. Yes, yes. Someone just for fun donated. Great, right? But that is basically that is exactly the bug that's going on here. Okay. that's it for this short Certora verification language tutorial. Here's a bunch of interesting links if you want to use the prover. Get yourself a Certora key. It's a thing that you need to be able to send things to the cloud. We're also open source, so if you want to be a contributor to the prover, by all means, you can do that. There is an installation guide. We have a lot of more tutorials, etc., etc. And if you want to use it, please do so. Also, there might be another interesting factor that plays in here, namely that we're hiring specifically for formal verification engineers. If you want to help protect DeFi in this way, please let me know. You can come to me. We have a booth today too, so please visit. And you can find me on Telegram if you have any questions. If you're interested in the work that we do at Certora, please connect and let me know if you have any questions. Thank you, guys.
Thank you very much for this explanation. Do you have any question?
So one thing I'm wondering about is reverts. So like in your power voting example, I couldn't easily find the code for the contract, but if someone tried to vote and send no tokens, would the call have reverted?
It depends. If you have a require, it would actually have been reverted. Something that I omitted from this tutorial is that whenever we symbolically call a function in a rule, the way I did it, just plainly calling it, the prover just checks all the computation paths that do not revert. If we want to include all of the computation paths that do revert, we have a keyword, namely we run, like instead of vote, we run vote at with revert. And that way we can also incorporate in the prover checks all of the revert cases. But what we want to do most of the time is in a successful run that changes, the states, we want to prove some invariance. Sometimes we also want to write rules about revert conditions. Like, for example, that's where the overflow comes in often, right? We want to make sure there is no overflow of something. We often find, of course, it's very easy for us to find any kind of unsafe casting with the prover. But yes, I omitted this part.
And so if you say check paths with revert as well, is a revert considered a satisfaction of the thing you're trying to prove, or a violation?
It depends on the property. If it can violate, if a revert can violate the property, it will find a violation.
But like in the power voting example, if we said check reverts as well, would the proof still have gone through?
For the invariant, I think so, yes, because I don't think that if a function just doesn't go through, then the sum wouldn't change. But it would still find the same counterexamples it found now.
Okay.
Make sense? A little, okay.
A little.
We can talk about it later if you want to.
Hi, thank you. So I was wondering, what are the computational requirements to run this software? Like, can it happen that your smart contract is too complex and then you just run out of time for proving?
We do encounter timeouts for very, very complex DeFi protocols with very, very complex properties that need a lot of computation paths. You saw like these like small examples are done in a minute or less. Of course, this is not the case for a lot of our clients. Like when we write rules for our customers, that might look a bit different. But most of the time, we still solve it. We have a lot of things going on under the hood to make formal verification actually tractable for the real world, which is really cool. But from time to time, there is such a thing as timeouts. Otherwise, we would make something decidable, which we don't, which we can't. So that's basically the gist of it. We have a lot of ways to tweak the prover, to tweak the underlying SMT solvers. the configuration files usually look much larger and have way more specifications than you saw just now for the complex programs. But from time to time, it's not possible to circumvent timeouts completely.
We don't have any time for question, but you can keep after. Thank you very much.
Thank you.